This video is a short discussion about continuous random variable. We know random variables are functions. They map outcomes from the underlying sample space to numbers. And how do we specify different types of random variables? We essentially look at how the probability values associated with different events generated by the random variable. And to describe how the probability are assigned to different events generated by a real value random variable, we can choose to look at the CDF function fx, which is defined by the probability value of x, random variable x, smaller or equal to a small x from the real line. In this video, we are going to introduce one specific example such that the CDF function is not only continuous but also differentiable, and is one continuous random variable example. Let's keep throwing a 10-sided fair die with numbers 0 to 9 on each side of this die without stopping. So it's not hard to guess that we would have outcomes such as a non-stopping sequence, right? With each digit either equal to 0, 1, 2 until 9. Let's consider this map, this function. Let's map these outcomes to numbers within 0 and 1 where the decimal expression, so this random variable x, would map a arbitrary outcome, for example a here, to point A. And we follow the convention such that 0.9999, if you have all the digits equal to equal to 9, it's equal to 1. We will consider that is a decimal expression of number 1. Now here comes the first question. What is the probability of this event, x equal to 1? You can pause the video at this moment and try to figure this out yourself. Well, it's 0, which is a not very surprising result because to have a 1, we need to make sure for this non-stopping throwing, we have to have a 9 at each throw. And given each throw is independent from each other, that essentially will be a product of infinitely many 1 over 10. That's no doubt will be 0. Actually, not only for 1, but for arbitrary numbers a here, the probability of x equal to a specific number is always of probability 0, because there's countably many values within the interval 0 and 1. Therefore, the probability of that you can get a specific exact number is always 0. Well, let's consider the second question. Now, how do we characterize the distribution of this random variable x? For example, how likely is the event that this random variable x takes value smaller or equal to 0.5? You can pause the video at this moment and try to figure this out yourself. Let's analyze the event first. Well, we know x smaller or equal to 0.5 contains all outcomes such that the first row is not a 5. It has to be smaller than 5. Right? So you can take as 0, 1, 2, 3 until 4. And there's also one specific outcome such that the first row is a 5 and all the remainings will be 0. Therefore, the probability of x smaller or equal to 0.5 will be the summation of the probability of these two mutually exclusive events. The first event is the first row is strictly smaller than 5. And we know for a 10-sided fair die, that's 0.5. Right? You have 5 possible outcomes to have out of 10 for the first row. As for the second one, a specific outcome that only have the first row equal to 5 and all the remainings are 0, we know to have such a specific outcome is always 0. So altogether, the probability of x smaller or equal to 0.5 is equal to 0.5. Actually, this relation is arbitrarily true for any number within 0 and 1. The probability of x smaller or equal to a is equal to a. Right? This probability function assigns this event, assigns a to such event x smaller or equal to a. Now let's discuss how to prove this identity. Let's cut 0, 1 into 10 to the power 1 gray. So here we have power 1 equal to 1. 10 grays such that each grade can be expressed as a closed interval from xi minus 1 with power 1 and xi 1, okay, with I equal to from 1 to 10. And each xi can be denoted in this format. For arbitrary, each xj can be denoted as j times 10 to the power minus 1, with j from 0 to 10 to the power 1. For example, if we choose I equal to 2 here, then we have this interval to denote the second grid, which is from point 1 to point 2. Right? So basically we cut 0, 1 into 10 pieces from 0, then end the first piece from 0 till point 1, the second piece from point 1 till point 2, and keep going. It's easy to check that the probability is in the union of those grays, those intervals, is the probability of x smaller or equal to xi, which is I times 10 to the power inverse. And for each grade, specifically, the probability of x takes value within each grade, given these grades are of the same length, is not very hard to check that the probability of x takes values in those grades will be 0.1, which is also 10 to the power minus 1. Right? For example, we can take a look of the first interval, first grid, which is from 0 and 0.1. Well, to consider the probability value of x takes value within such grade, that is basically saying that the first row has to be strictly smaller than the first row has to be let's see, the first row has to be strictly smaller than 1, so you have to have outcomes of such format 0, and we don't care what happens in the following. Plus, there contains a lot of outcomes like in that format. The second one will be you get 1 in the first row, but for all the remainings you have to have 0. As we have already discussed, the probability value of such event is always 0. Well, for this one, the probability of the probability of that the first row is a 0. That's 1 over 10. Right? 10 to the power minus 1. It's very easy to check in this simple example. So now we consider to approximate the probability value of x smaller or equal to a with this function. So basically, here we have 10 pieces. And suppose A is at this position. So suppose A is belong to IJA. I'll use JA to denote the index of the grid containing number A. And we're gonna use the probability of X takes values within those intervals to approximate the probability of X strictly smaller than A or equal to A. If A, for example, is right here, right on the boundary, so A is from both, for example, here is both F3 and F4 interval, then the choice is we choose the minimum index among these two. So in such case, when we have boundary case, we use this to denote the probability, to approximate the probability of X smaller or equal to A. Which actually in such case, that is exactly the probability of X smaller or equal to A, okay? When you have the boundary case like this. From the graph here, it's not very hard to check that the approximation is not always exact, but it's very close to the value we care for. Right? The difference between the targeted value here is always smaller than 10 to the power minus 1. Actually, if it cut into more pieces, for example, 10 to the power n grays, and we follow exactly the same procedure, we know the approximation is getting better, and the difference between this approximation and our targeted value, the probability value of X smaller or equal to A, is getting even smaller, right? If we take a close look of this summation, what happens to it if we let n grows larger and larger and larger? Note, this summation is essentially an integration from 0 to A with 1 as the integrand, which is equal to A. So indeed, we have proved that the probability of X smaller or equal to A should be equal to A for arbitrary value from the 0 and 1 interval. And particularly, we have a very special CDF function here. Right? It's not only continuous, but also differentiable. It's very smooth. We can rewrite 1 as the derivative of the CDF function, actually. So here we have two ways to represent the probability value of X smaller or equal to A. We could use the fx CDF function. We could also use this small fx. It's referred to as the density function, probability density function, PDF. So we have two different ways describing the distribution of X. And particularly, there exists a probability density function, fx. If we integrate this density, we have the mass. Right? If you integrate the probability density, you have the probability value. And from the example we have discussed, that if our interval has positive density function, different positive density function values, in the above example, we know this density function equal to 1 for arbitrary values from the 0, 1 interval, and there are countably many possible values in such interval that could be taken by X. This is actually the definition of continuous random variable. Okay, for any real valued random variable, such that if they has a non-negative function fx, satisfying this above Riemann integral condition, then this real value random variable is a continuous real value random variable. So in the example, we see that we can choose fx right equal to the derivative, first derivative of the CDF function, which is simply 1 for all the values from the 0, 1 interval. And there are countably infinite many possible values in 0, 1 taken by x. Well, for any discrete random variable y, if we consider arbitrary fy, we know they are discontinuous and jump functions. If we take derivative almost everywhere, their derivative is simply 0. And there is no fx we can find to satisfy the above identity via the Riemann integral. Also, for discrete random variable, there are at most countably many possible values taken by y, but here, in the building example we show in this video, there are uncountably many possible values taken by x. This is a short video introducing continuous random variable where one example. Hope you enjoy it. Thank you for watching this video.